Imagine you got stuck there where it's like automatically just shoots out water every like 10 seconds.
It's like malfunctioning, just keep spraying water.
Hello everyone, my name is Annlisa. I am a SARC tutor and I am here for the review session for Chemistry Fundamentals 1A, CHM 2040. And this is not like a regular tutoring session. I will go through some practice problems and I will explain the contents in between. I hope you guys already have the review packet that I posted online, or you can pull it up from the Study Union website, ucfstudyunion.wordpress.com, and go to the link chemistry and you can find the session and my name and the file will be there. So you guys are fine? So it's going to be a 2-hour session, and the review materials, some important review materials are also like towards the end of the review packet, so you can see that or you can use that for your further studies. So I'm going to start now. So the first question is, which of the following is a homogeneous mixture? So the matter can be classified to pure substance and mixtures. So the pure substance can again classified as elements or compounds, and the mixtures classified as homogeneous or heterogeneous. Okay, so my question is, which of the following is a homogeneous mixture? First option, iron block. What do you think about that? It's just iron inside that block, right? It's just iron, atoms of iron are present there. So that is going to be a pure substance. What about the slice of pizza? It's going to be like a mixture of so many compounds, right? Many carbohydrates will be there, proteins will be there. So it is like a mixture. And what about the composition? It's not like evenly in the slice of pizza, right? There will be like carbohydrates is more in some part and protein will be more in other part. So it is going to be an heterogeneous mixture. What about bronze? It's an alloy of two metals. But alloys are like homogeneous composition, so you can find the same percentage of each elements in like every section of that substance. So our answer is going to be C, bronze. And let's look at the option D, sodium chloride crystals. Is it just the sodium chloride compound, the molecules of NaCl? So that is going to be a compound, okay, compound or molecule. So first option is an element, and the second option is a heterogeneous mixture, and third option is our answer, the homogeneous mixture, and D, sodium chloride is a compound, like pure compound.
How do we know that bronze is a homogeneous mixture?
It's an alloy of two metals. It's a I think it's copper and tin. So metal alloys are homogeneous, okay? And the next question is, at what temperature Celsius scale and Fahrenheit scale reads the same? So we have to use the conversion equation between the Celsius scale and Fahrenheit scale. So C is equal to temperature in Fahrenheit scale minus 32 over 1.8. Okay, so the question is asking for at what temperature both scale reads the same temperature. Okay, so I'm going to put the variable x for the temperature. So for C and the temperature in Fahrenheit scale, that's going to be x, right? Because it's going to be same in both scale. So x is equal to x minus 32 over 1.8. So when you do the math, 1.8x will be equal to x minus 32 and 0.8x will be equal to negative 32, and our answer, the temperature will be negative 32 over 0.8, and you will end up with negative 40. It can be degree Celsius or degree Fahrenheit. You guys have a calculator, right? You can double check the answers.
Where does the 0.8 come from?
I brought this x towards this side, so 1.8 minus the 1, or probably you guys are doing like 1.8x and you have to get rid of this x from this side, so
Gotcha.
minus this x that side, do the same thing in the other side of the equation. That way you will end up with the 0.8x, okay? So our answer will be negative 40. Which option has the highest number of significant figures? So when you count the significant figures, the trailing zeros are not significant, but they are significant if they are after a decimal place, okay? But they have to follow a non-zero digit also. For our first option, 0.000546, these zeros are not significant because it's after decimal point, but before the decimal point it's not a non-zero digit, it's 0. So these zeros are not significant, but 5, 4 and 6 are significant. So it's gonna give you 3 significant figures, okay? For the second option, every non-zero digits are significant. 1.7, so 1 significant and also 7 is also significant. 2 significs are there. For 320 grams, see there is a decimal point here. So this decimal point makes this zero significant, okay? So you have 1, 2, 3 significant figures. For the option D, 1.006 grams. These zeros are in between two non-zero digits. So zeros between two non-zero digits are significant. So you have 1, 2, 3, 4 significant figures. So our option D is our answer. Do you have any question?
Yes. So for answer choice C, if there wasn't a decimal after the 0, it would just be 2, right?
Yep.
The 0 would be significant.
0 will not be significant. So next next question is round the answer to the correct significant figures and unit. So let's just count the significant figures first. For the first option you have 1, 2, 3, 4, 5 significant figure, and the second term has 1, 2, 3 significant figures. Third term has 1, 2, 3, 4 significant figures, and this fifth and the fourth one has 2 significant figures, okay? So in the numerator it is multiplication, right? 12.031 times, 8.06 times, 7.968 times, 2.1. So when you do the multiplication, you have to round your answer with the least number of significant figures. So your numerator has 2 significant figures, okay? You have to round your numerator. Your numerator will have the 2 significant figures. But when you do the math, if there is further calculation, don't round in between, but track the significant figures, okay? and the denominator is 13.0231 plus 12.01 centimeter. So this number has 1, 2, 3, 4, 5, 6 significant figures, and this one has 1, 2, 3, 4 significant figures. But this is an addition problem. So when you do the addition or subtraction, you have to round your answer with least number of decimal places. So this number has 1, 2, 3, 4 decimal place, and this one has 2 decimal place. So for the denominator, your answer will have 2 decimal places, but the addition, this is 13 point something plus 12.0. So there will be 2 numbers before the decimal place also. So your denominator will have 4 significant figures. And your final answer is the division, division of the 2 significant figure number with the 4 significant figure number. So your answer will have 2 significant figures at the end. Okay. So when you do the math, you will end up with 64.8 something. So your answer must have 2 significant figure. So when you round 64.8 to 2 significant figures, you can get rid of this 8, but this 8 is greater than 5. So the number before that will goes up by 1. So you can round your answer as 65. So you got the numerical part. And let's look at the unit. So this is multiplication, centimeter times centimeter times centimeter times centimeter, right? Multiplying centimeter 4 times. So you will end up with centimeter to the power 4 numerator over, this is addition, centimeter plus centimeter. So it's going to be centimeter. So you will end up with centimeter cube, right? Power of the numerator minus power of the denominator. So this is going to be 65 centimeter cube. You guys are okay?
So with division, is it the lowest amount of figures too?
Yeah, multiplication and division, lowest number of significant figure. Addition and subtraction, lowest number of decimal places. Just give me a second. So next question, which will displace the largest volume of water when you place 20.0 gram of iron block with density 7.86 gram per centimeter cube, or an aluminum block of mass 60 gram with density 2.70 gram per centimeter cube. So they are we are given the density, and also mass is also given, and the relation between mass and density is equal to mass over volume, right? So we have to figure out which of these metal will displace largest amount of water. So when you do the cross multiplication, you will end up with volume will be equal to mass over density. So these are given in centimeter cube, right? The volume is given in centimeter cube. 1 centimeter cube is same as that of 1 milliliter. Okay, so for liquids we will say volume in milliliters, and for solids the volume will be in centimeter cube. Okay, so you guys have to remember this conversion. 1 centimeter cube will be same as that of 1 milliliter. And when you when you put something in water, if it like sink or float, it will displace that much amount of volume. Like how much amount of volume it has to stay there, that will be displaced by that block or whatever be the substance. Okay. So for the iron block, V iron will be 20.0 grams divided by 7.86 gram per centimeter cube. So you will end up with 2.54 centimeter cube, which is same as that of 2.54 milliliters. Okay. For aluminum, it will be 60 grams divided by 2.70 gram per centimeter cube. (22.22 milliliters). So aluminum will displace the largest amount of water. So this equation, density equal to mass over volume, that's an important equation. So you have to use this equation for other calculation parts also, for stoichiometry and also for thermochemistry, everything. Okay, remember this equation. So question number 5. Following are the mass of a 12.0 gram glass block weighed by 4 groups in consecutive trials. Which group has the precise and accurate measurement? So we can go through each option and we can figure out that. Okay. So in option A, the measurements are 8.9, 9.0, 13.1, 12.9, and the average is 11.0. So these measurements are like random numbers, not in a consistent manner, right? You have 8, 13, and 12, so it's not a consistent measurements. So you can say it is not precise, and the average is 11.0, and the actual mass is 12.0. So the average is also not like closer to the your accurate value, so it is not precise and also not accurate. And option B, 10.9, 11.6, 14.7 and 10.5, and the average is 11.9. These measurements are also not consistent, like it's here and there, the values are here and there, but so it's going to be not precise, but the average is 11.9, and the accurate value, the original mass of the glass block is 12.0. So the average is more closer to the accurate value. So we can say it is accurate. The measurements are not precise but accurate because you got the average closer to the actual mass. For option C, 9.6, 9.8, 9.3, 9.4, and the average is 9.5. So the measurements are like consistent, like more closer, 9.3, 9.4, 9.5, so they are more closer. We can say these options are precise because these measurements are closer, and then the average is 9.5. That is more far away from 12.0. So this option is precise but not accurate. The final option, 12.3, 11.9, 12.1, 12.2, and the average is 12.1. So these values are like almost closer to each other, 11.9, 12.1, 12.2 and 12.3. So they are like consistent measurements. So we can say that is precise, and the average is 12.1, closer to the accurate value. So that is accurate also. So the answer is D, 12.3, 11.9, this one. Okay.
Could you say what precise means again? So it's like the measurements are close together?
Yeah.
Precise. Okay.
It doesn't matter if it is closer to the accurate value or far away from the accurate value, but the measurements, between the measurements, those will be like closer to each other.
Thank you.
How many protons, neutrons and electrons are there in a neutral calcium 40 atom? So if you see a symbol like this, Ca40, that 40 is going to be atomic number. I'm sorry, mass number. Mass number, okay? So when you write the symbol of an element, you will put the symbol for its name, and then in the left bottom its atomic number. Calcium atomic number is 20, and the left top its mass number. Okay, so atomic number, which is C, and mass number Z will be equal to number of protons for a neutral atom. For a neutral atom, the atomic number will be equal to number of proton, and if its charge is 0, it has to it will have the same amount of negative charges. Proton is positively charged, electron is negatively charged. So if the atom is neutral, there will be same number of proton and same number of electron. So the number of proton will be equal to number of electron in a neutral atom. Okay, and the mass number will be the sum of proton and neutron. So calcium, its atomic number is 20, so number of proton will be 20. It's a neutral atom, so number of proton will be same as that of number of electron, so electron is also 20, and mass number is the sum of proton and neutron, so number of neutron will be 40 minus 20, which is mass number minus atomic number, you will get 20. So our answer is C. Number of electrons present in manganese with a positive phi charge, manganese ion. So the positive charge means it lost electron. How much electron lost or how many electron lost, that will be equal to its charge. Okay. So in a neutral atom, the proton and electron are same. So if you remove electron, there will be more positive charge. You are removing all the negative charges, so the positive charge will be more. That's why it will end up with a positive charge. And metals will have the positive charges. They will form the positive cations. So for neutral manganese is 25 Mn. Its atomic number is 25, so the number of protons will be 25 and number of electrons also 25. But now its charge is positive 5. That means it lost 5 electrons. It lost 5 electrons. So For neutral manganese, number of protons will be 25, number of electrons will be 25, but for Mn positive 5, number of protons still the same, 25. You are not removing any proton. If you remove the proton, the element will change because atomic number is the identity for the element. But the number of electrons will be, it lost 5 electrons. So 25 minus 5, which is 20. So answer is B. Carbon has two naturally occurring isotopes. C12 has a mass of 12.000 AMU and abundance of 98.93%. C13 has a mass of 13.0034 AMU with a percentage of abundance 1.07. Find the average atomic mass of carbon. So if you have the information about the atomic masses of isotopes and their percentage of abundance, the average mass of that element will be sum of the product of that atomic mass with the percentage of abundance. So for carbon 12, its average mass will be mass of carbon 13 times its percentage plus mass of carbon 12 times its percentage of abundance, okay, and the percentage you have to use that in decimal. So 1.07% means that is 0.107. Sorry, 0.0107. So carbon 12 will be equal to 12.0000 times its percentage abundance, which is 0.9893 plus let's put 13 here and 12 here. I put the wrong order. So, and for carbon 13, it will be 13.0034 times its percentage of abundance, which is 0.0107. So you will get an answer about 12.0107. Okay, so our answer is going to be 12.0107 AMU.
Can you move this side? I just
Oh,
want to copy
sorry.
that. Thank you.
So atomic mass of that isotope times its percentage of abundance. If there is 3 or 4 or 5 isotopes, you have to multiply the mass of the isotope with its percentage and then add everything. You will get the average mass of that element. Okay. So next question, the average atomic mass of copper is 63.55 AMU. Copper 65 with a mass of 64.978 AMU has an abundance of 30.83%. What will be the mass of the other isotope copper 63? So you have the average mass of copper, which is 63.55 AMU, and you have the atomic mass of one of the isotope, which is copper 65 with 64.9278 AMU, and you just know the other isotope, copper 63. And the question is, we have to figure out the mass of this isotope copper 63. So it has two isotopes, right? So if you have the percentage of abundance of one isotope, you can figure out the percentage of other isotope by subtracting the given percentage from 100. So the percentage of Cu63 will be 69.17 percentage. Okay. Sometimes it will not be given, so just 100 minus whatever be the percentage of given isotope, you will get the percentage of other isotope. Okay. If there is 3, percentage of 2 of them will be given, and you just look for the third one. Okay. So this 63.55, if we follow this equation, this 63.55 will be mass of copper 65 times its percentage plus mass of copper 63 times its percentage, which is copper 65 has mass of 64.9278 times its percentage is 30.83. Use that in its decimal form, so it's going to be 0.3083 plus, you don't know the mass of copper 63, that is what we have to figure out, and times its percentage 0.6917. So this will be equal to 63.55 minus 20.0172 plus copper 63 times 0.6917. Okay. So the product of atomic mass of copper 63 and its percentage will be the difference between the average mass and the product of the other isotope given, right? So you will end up with 43.55375 will be equal to mass of copper 63 times 0.6917. So mass of copper 63 will be equal to 62.9358. So if you round, it's going to be 5896. Don't worry about the negative sign, okay? So it's 62.935896. So if you round with the 4 decimal places, you have to get rid of this 9. So this 62.935896. I think some calculation error, so it should be like 599. So if you get rid of this 9, it will be like goes up by 1, so you will end up the answer like 62.9360. So our answer will be 62.9360. Okay. So if you if they are given the average atomic mass and the percentage and mass of the other isotope, you can figure out the mass of the asking isotope with the same equation that we used earlier. Okay. So in the following options, 24 moles of which element weigh the least? So they are already given the number of moles. It's like a constant number for each of the element. So atomic mass expressed in grams will be equal to the mass of 1 mole of that element, right? So for copper, its atomic mass is around 60s, and lead, xenon and zirconium are like far end of the periodic table. Do you have the periodic table with you? Yeah, so you can double check the masses there. So copper is like the left side on the top, and the can I borrow the periodic table? So you have copper, which is 63.546 grams per mole. So 1 mole of copper will be 63.546. And the next option is lead, which is 207.2 grams. And then the xenon will be 131.29. So if you have the number of moles, the mass will be equal to number of moles times atomic mass. So copper has the least atomic mass, so that will weigh the least. Okay. How many oxygen atoms are present in 720.0 grams of glucose with formula C6H12O6? So you have the chemical formula, so you can figure out the molecular formula by adding the masses of each element present in that compound. So the molecular mass will be 6 times atomic mass of carbon plus 12 times atomic mass of hydrogen plus 6 times atomic mass of oxygen. Atomic mass of carbon is 12.01, and hydrogen you can use 1.01, and oxygen will be 16. So 6 times 12.01 plus 12 times 1.01 plus 6 times 16. So you will end up with an answer 180.18. Okay. So molecular mass of C6H12O6 will be 180.18 gram per mole. Okay. And you have to figure out how many moles of glucose are there in this 720 grams. So 720 grams times 1 mole is equal to 180.18 grams. So you will get the number of moles of glucose, but it is asking for how many oxygen atoms are present there. So in 1 mole of glucose there will be 6 moles of oxygen. It is same like in 1 molecule of glucose there will be 6 atoms of oxygen. If you convert that into molar form, it will be like in 1 mole of glucose there will be 6 moles of oxygen atoms. Okay. So 6 moles of oxygen in one more. Lithium is a metal and chlorine. So when you get like a formula for a compound, if you have to add nitrous acid. Nitrous acid. So when you name oxyacids, if the polyatomic ion present in that compound, oxyacids has the polyatomic groups, the groups in this chart. Okay. So if the name of the polyatomic molecule ends in ATE, the suffix will be ic. Okay. But if the suffix for the polyatomic ion is ITE, like sulfite or chloride, like that, then when you name that acid, that is going to end up with OUS, chlorous acid, or sulfurous acid. So in this option we have nitrous acid. Since it starts with the polyatomic ion, you can conclude that there will be a polyatomic ion, but nitrous, so the OUS is going to be for the polyatomic ion end with ITE. So it is nitrous, so the polyatomic ion present will be nitrite, which is NO2 negative. Okay. You have hydrogen and this NO2 negative. Hydrogen usual charge positive, and nitrite, its usual charge is -1. Switch that and you will end up with HNO2. But this option is HNO3. This NO3 is the other polyatomic atom, which is nitrate. So if you name this option HNO3, you have the polyatomic group nitrate, ATE, ends in ATE. So it will end up with nitric. Get rid of the ATE and put IC, nitric acid. So this is the wrong match. If the molecular mass of a compound with phosphorus and oxygen is 283.88, what is the molecular formula if the compound contains 43.64% by mass of phosphorus? So you have to figure out the empirical formula first, and then figure out the empirical formula mass, and then from that you can figure out the molecular mass of that compound. So to figure out empirical formula, you have the elements phosphorus and oxygen. The percentage of phosphorus is given, which is 43.64%. Or you can say in 100 grams of that compound there will be 43.64 grams of phosphorus. So the number of moles of phosphorus present will be 43.64 grams divided by its atomic mass, which is 30.97, and the number of moles of oxygen will be, if you have 43.64% of phosphorus in that compound, then the percentage of oxygen will be, subtract that from 100, it will be 56.36 over the atomic mass of oxygen, which is 16. So for phosphorus you will end up with 1.41, and for oxygen the number of moles will be 56.36 divided by 16, which is 3.5. So this 1.4 you can round it as 1.5, and this is 3.5, and actually you have to divide the largest number of moles with the least number of moles. So to get the ratio between the number of moles of each element. So then it's going to be 1.41 over 1.41, and oxygen 3.5 over 1.41. Okay, so you will end up with P1, and oxygen 3.5 over 1.41, it's approximately 2. So P1 O2. So you don't have to further multiply that because it's almost like you will end up with almost an integer. So get the empirical formula mass. So that is going to be 62.97, and then the molecular mass is already given 283.88. So the empirical formula will give you the simplest form of that compound. The number of atoms of each element will be simplified to the least number. So to figure out the constant with which you have to multiply the empirical formula, to get the molecular formula, you have to divide the molecular formula mass by empirical formula mass. So 283.88 over 62.97. Which is equal to 4.5 3.88 62.97. So and then you have to multiply your empirical formula with the constant. It is going to be approximately 4, and you will end up with the equation P4 with the formula P4O8. I'm sorry. P4O8. It's supposed to be this option, but the option is wrong. P4O8. Okay. Hmm?
4.5 doesn't it round to 5?
She's multiplying by 4.
Let me double check the calculation one more time. 43.64 divided by 30. Yeah, this one is supposed to be 2.5. This one was supposed to be 2.5. This one P1 or 2.5. So here you will end up with a decimal. Then you have to get that ratio in a integer. So you have to multiply with 2. So you will end up with P2O5 because you have to multiply with 2, the empirical formula. So you will end up with P2O5. This will be the empirical formula. Okay, and when you get the mass for the empirical formula, it will be 30.97 times 2 plus 16 times 5, which is 141.94. So when you get the ratio for the molecular mass and the empirical formula mass, you will end up with 2, integer 2. Okay. I'm sorry. The molecular formula mass is already given 283.88. So when you divide 283.88 with the 141.94, you will end up with 2, approximately 2. So you can round it up to 2. So this is the constant that you have to multiply the empirical formula. So you have to multiply P2O5 with 2. Multiplication means you have to multiply the subscript. So you will end up with P4O10. So our answer is P4O10. I'm sorry for the confusion. Okay. And next is balancing. So you have the equation C3H8O plus O2 gives you CO2 plus H2O. So you have to make sure the number of atoms of each element is same in both sides. So first just write the elements. So you have carbon, hydrogen and oxygen. In the reactant side you have 3 carbon and the product side you have 1. And in the reactant side you have 8 hydrogen and product side you have 2 hydrogen. And in the reactant side you have 2 plus 1, 3 oxygen, and product side you have 2 plus 1, 3 oxygen. So first balance elements other than hydrogen and oxygen. So you have 3 carbon here, only 1 in the product side. So you have to make it equal to 3. So you have to multiply with the constant 3. So when you multiply with the constant, you have to put that number as the coefficient.
Sorry, I can't see. What are the subscripts?
C3H8O. C3H8O. So you have to put the integer as the coefficient for the compound that has the carbon. So it will be 3CO2. And then when you put the coefficient 3, that's going to change the number of oxygen to 6. And then you have to balance hydrogen. You have, yeah, because 3 times, 6 plus 1, 7. 3 times 2, 6 plus 1, 7. And you have 8 hydrogen in the reactant side and 2 in the product side. So to balance that, you have to multiply with 4 in the product side, put that 4 as coefficient for hydrogen, and that's going to change the number of oxygen from 6 plus 4 to 10. Plus 1, 3. And you have to make the number of oxygen equal in both sides. So this is 3 and this is 10. But this 3 oxygen is in this compound and there is O2. So basically you have to change the number of oxygen. The you have to put the coefficient for this O2. You cannot put coefficient for this compound, okay, because it's already balanced. So these 3 is like 2 is from oxygen and 1 is from this compound. So to get 10, this one must be 9 and this one is 1, right? So 9 plus 1. So you have to put the coefficient, you have to get 9 in this side, so you have to put the coefficient 9 over 2 for this oxygen. So C3H8O plus 9 over 2 O2 gives you 3 CO2 plus 4 H2O. But this is like a fraction. You don't need fraction in your balanced equation. So to get rid of this 2, you have to multiply the entire equation with 2. So you will end up with the formula equation, chemical equation, 2C3H8O plus 9O2 gives you 6 CO2 plus 8 H2O. Okay. So I put the coefficient 9 by 2 for this oxygen because these 3, the oxygen is distributed between 2 compounds, in this compound and oxygen gas. So when you add this sum, you will end up with the 10, but you cannot change this one because other elements are already balanced. So you have to put the 9 by 2 O2, and to get rid of this fraction, instead of just multiplying coefficient of oxygen, you have to multiply the entire compound. Then only the equation will be balanced, and you will end up with 2C3H8O plus 9O2 gives you 6O2 plus 8H2O. Okay. The answer is already given. So next is like a stoichiometric problem. If in the previous reaction, if 18.65 grams of propanol reacted with 24.64 grams of oxygen, the amount of CO2 obtained is 19.08 grams, which is true for the reaction. So you have to figure out the limiting reactant, theoretical yield, and the percentage of yield. So from the coefficients, it's going to be like 2 moles of C3H8O reacts with 9 moles of O2, gives 6 moles of CO2 and H2O. So they are given the mass of C3H8O reacting, which is 18.65 grams, and oxygen is 24.64 grams, and you will end up with CO2, which is 19.08 grams. This is your actual yield. Okay. You have the information about 2 reactants, but you don't know which one is a limiting reactant and how much product will be formed. The amount of product that's going to form depends upon the limiting reactant, and that amount will be your theoretical yield. So to figure out the theoretical yield, you have to convert the grams of each reactant to the product they are asking, which is CO2. So 18.65 grams C3H8 times, you have to figure out how many moles is that. So C3H8O, its molecular mass is 60.03 grams times, when you convert the moles of one compound to the another, you have to use the coefficient as the conversion. So you need the moles of CO2 at the end. So you will get 6 moles of CO2 if 2 moles of C3H8O is when 2 moles of C3H8O is reacted. Okay. And once you get the moles of CO2, you have to convert that into grams of CO2. Molecular mass of CO2 is 44.02 over 1 mole. Okay, and this will be somewhere around 18.65 times 6 times 44.02 divided by 60.03 divided by 2, 41.02 grams, 03 grams. Okay, and for oxygen 24.6402, and the number of moles will be 1 mole. This is oxygen molecule, so you have to use 32 grams times, with 9 moles of oxygen you will get 6 moles of carbon dioxide. So 6 moles of CO2 over 9 moles of oxygen times 44.02 grams over 1 mole. It is 22.60 grams. So the least amount of carbon dioxide formed will be the theoretical yield. So you have to figure out how much carbon dioxide will be formed with each amount of reactant given, and the least number will be the theoretical yield. Okay, so the reactant that gives you the least amount of product will be your limiting reactant. If this one is limiting reactant, the other one will be excess reactant or excess reagent. Okay, so we figure out the limiting reactant and the theoretical yield and also the excess reactant, and next is percentage of yield. Percentage of yield is the ratio between actual yield over theoretical yield times 100. So 19.08 over 22.60 times 100. Which is 84.42%. There will be some rounding difference, so just figure out the best option. Limiting reactant oxygen and theoretical yield 22.59 and the percentage of yield 84.5. So the entire stoichiometric problem. The reactant that gives you the least amount of product will be the limiting reactant, and the least amount will be the theoretical yield, and the actual yield will be in the question. So to get the percentage of yield, actual yield over theoretical yield times 100. And when you convert the moles of one compound to the another, you have to use the coefficients in the balanced chemical equation. Always make sure the equation given is balanced. What is the molarity of the solution prepared by dissolving 87.0 grams of lithium nitrate in 500 ml of water? Molar mass of lithium nitrate is 68.95 grams per mole. So you have the mass of lithium nitrate and the volume of water you are using, and it's asking for the molarity. Molarity is equal to number of moles over volume in liters. So you have to figure out how many moles is this 87 grams, and then you have to divide that with the volume. 87.0 grams times molar mass is 68.95 grams, so 1 mole over 68.95 0.95 grams times, you have to divide the number of moles with the volume, which is same as multiplying with the reciprocal, and the volume must be in liters. 1000 milliliter will be equal to 1 liter, so 500 milliliter is 0.5 liter. So you will end up with 2.52 moles per liter. Actually 2.52. So get the number of moles and divide with the given volume of solution. The molarity of 50 ml of lead to nitrate needed to completely reacted with 50 ml of 1.25 molar iron 3 chloride. So you have the compound lead to nitrate, its charge is positive 2. So its formula is going to be, nitrate has symbol NO3 negative and lead is Pb2 plus. So when you interchange, you will end up with PbNO3 twice plus iron 3 chloride, which is, iron has positive 3 charge and chlorine is negative 1 charge. Interchange, you will end up with FeCl3, gives you, so this is like two ionic compounds reacting, so just switch the anionic part. So the product will be lead chloride and iron 3 nitrate. The formula for lead chloride will be PbCl2. Pb has the positive 2 charge, chlorine negative 1. Interchange, you will end up with the formula PbCl2 plus iron has the positive 3 charge and nitrate has negative 1 charge. So when you interchange, you will end up with FeNO3 thrice. So it is not balanced and you have to balance that. So you have 1 Pb, iron, chlorine and nitrate. This side 1 lead, iron, and this side also 1. Here is 1 iron in other side also. There is 3 chloride ions. Here you have 2 chloride ions. Here you have 2 nitrate ion and here you have 3 nitrate ion. So if in both side it is like different numbers, but there is only one compound that has that molecule, you can just multiply with each other. So this side you have to multiply with 2 and this will be 3. So first balance chlorine, and that is going to eventually balance the other molecule also. So if you put the coefficient 2 here and the coefficient 3 here, so 2 FeCl3 and 3 PbCl2, that's going to change this 1 to 3 and iron here to 2. So if we put the coefficient 3 in left side for lead, that's going to change this to 6, nitrate to 6. And if you put the coefficient, when you put the coefficient 2 here, this changes the iron in right side to, so you have to multiply the right side of iron to 2, So when you put the coefficient there, that's going to eventually change the nitrate to 6. So everything is balanced now. So balanced equation is 3 PbNO3 twice plus 2 FeCl3 gives 3 PbCl2 plus 2 FeNO3 thrice. Okay. So you have the volume and the molarity of iron 3 chloride. So you have to figure out how many moles is this 50 ml and 1.25 molar iron 3 chloride, and how many moles of nitrate, lead to nitrate you need to react with that, and then that's gonna, and then divide that number of moles with the volume 50 ml. So use the volume in liters. Okay. So 1.25 moles of FeCl3 in 1 liter, and its number of moles will be 0.05 liters over 1 times, convert the moles of FeCl3 to moles of PbNO3 twice, which is 3 moles of PbNO3 twice with 2 moles of FeCl3, and then you will get the moles of PbNO3 twice, and then divide that with the volume, but volume must be in liters, so which is 1 over 0.05 liters. Okay, and you will end up with the answer 2.55 molar. So our answer will be 2.55. Then next question is, which of the following is insoluble? So you have to use the solubility chart for that. That's also given in the review packet, and if there is like first group elements and nitrate group there, that is going to be always soluble, and there is some exceptions in that chart, so you have to review that chart. So first option is LiNO3, lithium nitrate. So you have lithium and nitrate, that's going to be soluble, and then barium sulfide. So for the solubility chart for sulfide, these sulfides are insoluble, but if it is with barium, that is going to be soluble. So this is also soluble, and lead sulfate. For sulfate, they are usually soluble, but if it is with lead 2+, that is going to be insoluble. So the insoluble compound is going to be PbSO4. And then NH4 twice CO3. If you have the ammonium ion, that is soluble, there is no exceptions. Okay. And this is the aqueous reaction between two compounds. So when there is like aqueous reaction, you can switch the anionic part, and if it is like a precipitation reaction, you have to put the subscript solid. So you have aluminum nitrate and sodium phosphate. Aluminum nitrate, in this compound it has +3 charge and nitrate is -1 charge. Sodium is +1 charge and phosphate is -3 charge. So when you switch the anionic part, you will end up with aluminum phosphate, which is AlPO4. This is negative 3 charge, positive 3 charge, so just cancel out. And sodium nitrate. Sodium is positive 1 charge, nitrate negative 1 charge, so it's going to be NaNO3. So sodium nitrate, that is soluble compound, aqueous. And for phosphate, they are usually insoluble, and if it is with the first group elements, that is soluble, but the cationic part is aluminum, so this is a precipitation reaction. You will end up with solid aluminum phosphate. So this one is like the similar problem, and potassium iodide and silver 1 nitrate are mixed. So potassium K plus and iodide I negative 1 charge, the formula will be Ki. This is a soluble compound, plus silver 1 nitrate. Silver, its for symbol is Ag and its charge is 1, positive 1. Nitrate is negative 1 charge. So when you interchange the charges, you will end up with the formula AgNO3. Nitrate is present there, so this is also a soluble compound, and then when they react, switch the anionic part, you will end up with potassium nitrate. Potassium has positive 1 charge, nitrate has negative 1 charge, so you will end up with KNO3, which is a soluble compound because you have the nitrate there, and also potassium, first group element, and then plus switch these iodide to silver, which is Agi. Iodides are usually soluble, but when they are with Ag plus, that is insoluble. So this is going to be a solid precipitate. So next question, the following reaction is occurring in a bomb calorimeter with heat capacity 1.56 joule per degree Celsius. What does the enthalpy change per mole of C6H12O6 if the temperature of the calorimeter changed by 30 degrees Celsius when 12.0 grams reacted? So you have the equation here, and then they are asking for if we react this 1 mole of C6H12O6, how much amount of energy will be released. So for the bomb calorimeter, the equation will be Q reaction will be equal to negative of Q calorimeter, and Q calorimeter equal to heat capacity of calorimeter times change in temperature. Heat capacity is given, which is 1.56 times the change in temperature, which is 30.0. So you will end up with 46.8 joules, and this 46.8 joules is given by this 12.06 grams of C6H12O6, and they are asking for the enthalpy change for 1 mole C6H12O6 when 1 mole C6H12O6 is reacted. So you have to figure out how many moles is this 12.06 grams. So 12.06 grams of C6H12O6 times 1 mole will be 180.118, and that will be equal to 0.06693 moles. So this many moles gives you 46.8 joules. So enthalpy change per mole will be equal to 46.8 joules over the number of moles 0.06693, which is equal to 699 joule per mole. So the reaction happening, the enthalpy change, heat energy for the reaction will be equal to the negative of Q calorimeter, and then for the Q calorimeter it is C delta T, and then plug the values you have. So figure out how many moles was there, and then divide the heat energy with the number of moles. You will get the enthalpy change per mole. And for next question, given the following thermochemical equations, and then you have to figure out the delta H for the following equation: 4NH3 plus 5O2 plus 4NO plus 6H2O. So this is like a review for the Hess's law. So you have to play with the given equation, and you have to end with the desired equation. So let's look at the equations. So in the first in the target equation, you need ammonia in the product side. So in the given equation, in the second one, ammonia is in the product side, but you need ammonia in the reactant side. That means you have to flip the second equation. So you have to flip it, and in the desired equation you need 4 moles of NH3, but here it is 2 moles of NH3, and you have to multiply with a 2, not just ammonia, the entire equation. So the new second equation will be, you flipped it and multiply with the 2. So 4 NH3 gas gives you 2 N2 gas plus 6 H2 gas. And for the enthalpy change, if you flip the given reaction, the enthalpy change will be opposite of that. If it is positive, it will be negative at the end, and if it is a negative enthalpy, it will be positive at the end. So since you flipped it, the delta H will be positive 91.8, and also you multiplied with a 2, so 91.8 times 2, you will end up with 183.6. Okay, and you need 4 NO in the product side, and in the given equation you have the NO. In the first equation you have NO in the product side also, so you don't have to flip it, but make sure the coefficient matches. So you have to make this equal to 4, so you have to times the first equation with a 2. So the new first equation will be 2 N2 gas plus 2 O2 gas gives you 4 NO gas, and the delta H for the reaction will be you have to multiply with the 2. So 180.6 times 2, 361.2. This one we flipped it, so you have to, we can say like multiply with the -1 and then multiply with the constant 2. And for the H2O, you need 6 H2Os at the end, and the given equation, the third one, H2O is in the product side, so just keep the direction the same but make sure the coefficient matches. So you have to multiply this equation with a 3. So same time multiply the enthalpy with a 3. So the new third equation will be 3H2 gas plus 3O2 gas gives you 6 H2O gas, and the delta H will be negative 483.7 times 3, which is negative 1451.1, and then add all this equation, and like similar to mathematical equation, if you have same terms in both sides, you can get rid of that. Let's consider these arrows as like a equal sign. So you have 4 NH3 here, reactant side, and there is no other NH3 in the product side. So this will stays the same, and you have 2 N2 in the product reactant side and 2 N2 in the reactant side. So 2 N2 in the reactant side and 2 N2 in the product side, so that will be cancelled out, and you have 3H2 you have 3H2 in the, so it's actually 6H2. H2 here, so 3H2 gas here and 6H2 gas. Is it really H2? So this will gives you 3H2 in this side, and just get the difference, and the difference will be put as a coefficient with the highest coefficient, okay? And then you have 3O2 and 2O2, and you will end up with the 5O2. So the final equation will be 4NH3 plus 5O2 gives you 4NO plus 6H2O. H2 plus O2 gives 4 times 3, 12, 12, 10, 4, 6, 10. It should be cancelled out. Did I miss something? H2, I put 3H2, 3O2, 4NO, and here flipped it. 6H2. Yeah, you're right, yeah. I think that's a typo, yeah. So it is 2H2. So then you will end up with 6H2 here, and it will be cancelled out, and you will get the final equation. And then since you are adding this equation, you have to add the enthalpies also, and make sure the signs, you have to follow the signs also. So you have to add 183.6 plus 361.2 plus negative 1451.1, and you will end up with 183.6 plus 361.2 minus 1. Negative 906.3 kilojoules. So when you flip the equation, the enthalpy change will be opposite sign, and when you multiply with the coefficient to make it equal with the desired equation, you have to multiply the enthalpy also.
When you went to balance in the beginning and you multiplied by 3 on the third one, you multiplied by a different number on the first one you did. When I looked at the original, I didn't see how you got those numbers to multiply by, like when you had to balance it.
So here it's 2NH3, right?
Yes.
So in the final equation you need 4NH3. So to make it 4, you have to multiply 2 with the 2.
Okay.
But not just NH3 but the entire equation.
Okay. But you're just picking out spots? Like you're just seeing what's like in both? Or?
Just look at the final equation you need. Look at the final equation you need, and then figure out the equation in the given reactions, and then flip it, or if you have to flip it, and then if you have to multiply with a constant, multiply with that, okay?
And each one's going to be, like each one we have to match perfectly with the given?
Yep, then only it will be cancelled out at the end, okay? So I think we can do the next question also, and then the 26, 27 and 28 is just like the previous examples, and if I don't get the time, I will post the answers in the student union website, okay? So in the question number 25, .00 gram sample of octane C8H18 is burned in a bomb calorimeter containing 1200 grams of water at an initial temperature 25 degrees Celsius. After the reaction, the final temperature of the water is 33.20 degrees Celsius. The heat capacity of the calorimeter is 837 joule per degree Celsius. The specific heat of water is 4.184 joule per gram per degree Celsius. Calculate the heat of combustion of octane in kilojoule per mole. So this reaction is happening in the bomb calorimeter, but there is a solution also present there. Water is also present there. So the Q reaction will be negative of Q solution plus Q calorimeter. It's not just the calorimeter, but there is solution also present, so you have to consider both. So Q reaction will be equal to negative of Q solution plus Q calorimeter, and for Q solution, you have to use the equation mc delta T, and Q calorimeter, you have to use heat capacity times the delta T. So the mass must be in grams, specific capacity is given, and delta T, change in temperature, it could be in degrees Celsius or change can be in Kelvin also, it doesn't matter because both is going to be same. So when you plug the values, negative 1200 grams times 4.184 joule per gram per degree Celsius times the temperature change is given, which is the initial and final temperature is given. So you have to get the temperature change. So it's going to be 33.20 minus 25, and then add the heat for the calorimeter, which is heat capacity times temperature change. Heat capacity is 837 joule per gram per degree Celsius times the same temperature change, which is 33.20 minus 25 degrees Celsius. So after the calculation, you will get an answer times 4.184 times 33.2 minus 25 plus 837 times 33.20 minus 25, negative 4833.96 joules. So like we did for the previous example, this much joules is given by this 1 gram sample of octane.
So did you use the Q equals MC times delta T?
For the solution.
And then why did you use the grams of water instead of the grams of CH18?
Because C8H18, the combustion of C8H18 is the reaction, and it is happening in the presence of in that solution. So the solution and the calorimeter is like the surrounding, and the reaction, the combustion reaction is the system. So you have to add the temperature, heat energy change for the surroundings to get the temperature, thermal change for the system. Okay. So this much joules is given by 1 gram sample of octane. So you have to convert the 1 gram to how much moles is that, and then you have to divide the joules with the moles.
You need the joules and kilojoules.
You can convert that like at the end also, that's fine. If you want to convert this right here, you can do that also. So it's going to be 1 kilojoule over 8,000 joule, so which is negative 48.03 kilojoule. So the molecular mass for octane is 114.08. So 1 gram C8H18 will be equal to 1 mole over 114.08 grams. Which is approximately 87.66 times 10 to the power of negative 2 moles. And then you have to divide the given kilojoules with the number of moles, so which is 48.033 divided by 87.66 divided by 10 to the power of, you will get 54.79 kilojoules, and the sign is negative. Okay, negative 48.033 over this much moles, you will get negative 54.79 kilojoule per mole. So when you try later, just make sure the calculations are right. So in the next question, calculate the mass of silver 107.91 gram per mole needed to react with Cl2 to produce 84 grams of silver chloride. Its molecular mass is given 143.36 gram per mole. The equation for this reaction is 2 Ag plus Cl2 gives 2 AgCl. So it's a stoichiometric problem. And make sure when you do the stoichiometric problems, it is balanced. It is already balanced. You have 2 silver here, 2 silver here, 2 chlorine here, 2 chlorine here. And it's asking for how much silver we need to react with Cl2 to produce 84 grams of silver chloride. So Cl2 in this question is considered as like excess product, excess reactant. So you need to get 84 grams of silver chloride at the end. So convert the moles of silver chloride to moles of silver and then figure out how much grams is that. So 84 grams silver chloride is same as 1 mole over 143.36 grams. And then moles of silver chloride to moles of silver, use the coefficients, which is 2 moles of silver over 2 moles of AgCl. This will cancel out, this moles of AgCl cancel out, and then you will end up with moles of silver. And to get the mass of silver, multiply with the atomic mass, which is 107.91 gram per mole. So 84 times 2 times 107.91 divided by 143.36 by 2. So it is going to be 63.2285 grams, and if you want to round with the significant figure, this one has only 2 significant figure, so final answer is going to be 63 grams of silver. Okay. So the 27 and 28, it's a stoichiometric problem and the Hess's law problem. So I will post the answers by tonight, so you can check that, and the answers for the other problems will be also posted, so you can double check the answers when you practice later. Okay. Thank you for coming for this review session. Thank you so much.
Will the